Hello, we're group 2, and today I'll be presenting on our work done characterizing nearby galaxies with Seagal. So, so to start out, I'm going to describe our sample. We used a selection of nearby galaxies from the Sings and Kingfish sample. We have shown here the two examples of the Hubble tuning fork diagram, so you can see that these galaxies span a range of characteristics. More specifically, the SING survey is the Spitzer Infrared Nearby Galaxies survey. The Kingfish survey is the Key Insights on Nearby Galaxies, a far infrared survey with Herschel. Both of these samples have been supplemented with additional observations that span from the far ultraviolet to the far infrared. So these galaxies, these surveys were designed to span a range of galaxy characteristics, which we'll discuss more later on. This is 61 nearby galaxies, so it's less than 30 megaparsecs away. In order to characterize these galaxies, we used the powerful SED modeling code called SIGAL, or the code investigating galaxy emission. So in order to use this code, you take observed photometry and/or spectroscopy, like that from Spitzer and Herschel, and supply input parameters like redshift, stellar population, including the star formation history and the single stellar population characteristics, dust characteristics like the amount of attenuation and emission, and nebular emission characteristics, as well as metallicity and a number of other parameters. After plugging in the observations and these input parameters, Seagal will find the best fit for those parameters between what we supply and the observations. We then get out a model SED, or spectral energy distribution, and a measure of the best fit parameters, so we can understand those characteristics of the galaxies. Additionally, we can get measures of emission line flux. So here we provide an example spectrum, so you can see in black the actual observations of NGC 3773. And this example is specifically handmade by our group in order to best fit those points. But of course, Seagal does more intense iterative technique. So you can see how the SED shown in red fits those points and attempts to replicate the observed photometry. So using the fits from the galaxies in our sample, we can plot the star formation rate against the stellar mass of these galaxies. You can see how there's really only a few values that comes from the fit parameters that we supplied to the code. And we can see that with increasing star formation peak, so that's when the peak of the star formation occurred, with more recent star formation showing up in yellow and more distant star formation showing up in that blue color according to the color bar. We can see that as there's more recent star formation, we have a higher star formation rate and a higher specific star formation rate, which is intuitive. So we find additionally that there are no current starbursts happening in this sample, but that there is active star formation. Cool. So in order to characterize the emission lines of these galaxies, we used Cloudy, which is a powerful SED modeling algorithm, which will produce a spectrum based on input parameters similar to those in Seagal, like metallicity and the ionization parameter. Cloudy produces emission lines that we can then use in the Seagal fits. So unlike Seagal, which is fitting a SED to observations, Cloudy is just producing an SED. There's no fit to observations. So you can supply it with an incident SED like that from an AGN or from a single star or a stellar population like shown in this cartoon. Combine that with parameters you provide of the nebular dust and gas, and you will get out a resulting SED, which is something you could perhaps observe. So with emission lines, with emission line measurements from Seagal and Cloudy, we plotted our data on a BPT diagram. This is not showing our data. This is just an example of a canonical BPT diagram where we show the ratio of ionized emission lines to H beta and H alpha. Based on models shown in the lines, that delineates regions where the ionizing source comes from OB stars in H2 regions, shown in that lower corner, whereas in the upper corner, the ionizing source is AGN. In between the lines, and you can see in the actual observed data, not from our sample, but from QLE 2006, that there can be a composite region where there's a blend between these two sources, or it's inconclusive which source is providing the ionization flux. Oh, I pressed the wrong button.
Right.
Press it.
Oh, you press B.
Cool. Yes. So here are our results. So this is a BPT diagram that we made using results from Cloudy. So you can see here, as with these annotations, you can see as you move along the tracks, there's increasing metallicity along those different dashed and solid lines. And then moving with the color bar, that's an increasing ionization parameter, which shows the ratio between the recombination rate and the ionizing rate. So based on where our observed emission lines fall from those galaxies, we can try to characterize those galaxies. So shown in the black stars are the actual measurements we have from our Kingfish and Sing sample. So we can see that some of those black stars are fit well by the input parameters we provided. So you can see that they span a range of ionization parameter as well as a range of metallicity. But some of those galaxies are not fit well by the input SED that we used. So with some trial and error, we reasoned that we had to change the input parameter. So this is just from an O star, but we changed our input parameter to an AGN input SED, which hit more of those points out there, showing us that our sample does contain AGN, as well as both low and high metallicity galaxies with varying ionization parameters. So confirming what we knew before, that this sample of galaxies is diverse and spans a range of characteristics. Ultimately, what have we learned? Well, we've learned how to fit SEDs to spectrophotometric observations using SIGAL. We've also understood what parameters go into constructing an SED and the interplay of those different variables, which ones are most important and have the highest impact on the shape of the SED, and how those parameters interact with each other to change the shape. And finally, we learned how to characterize these nearby galaxies with SED fitting and the BPT diagram. So thanks so much, and we'll all take questions now.
Questions?
It's a simple question, but how to define the recent active star formation and starburst? What's the difference?
From my understanding, and if anyone else wants to answer this question, you can, but a starburst is a concentrated peak in star formation, whereas I'm using the same words, but a starburst is a concentrated period of star formation, as opposed to a peak of star formation that is more spread out, but still does reach a maximum rate and then falls off. Does that make sense?
More questions? So about the cloudy grid that you use, what are the geometry parameters that you played with? The geometry of cloudy, yes.
Oh.
I mean, you have an inner radius, outer radius, you have density profile, all these kind of things.
About the density of the cloud?
Anything that define, the geometry
For
of
the
cloud?
cloudy simulations, we actually played with the ionization parameter and the metallicities, whereas for the density, as we didn't see much of a difference for like from the points you saw on the graphs, we actually stopped to make the density vary and fixed it to, I don't remember the parameter, but we didn't play much with the density of the cloud.
Okay.
So the main parameters we played with were actually the ionization parameter and the metallicity. Oh, and the SED. We tried with the OB star and the AGN SED. Yeah.
Okay, cool. Yes, so group 3.